friends, so today we are solving this problem, find the maximum number of fruits collected. So there is a game called Dungeon and comprised of the n cross n room arranged in a grid. Okay, so rooms are arranged in a grid kind of thing. So 2D array would be given is basically, and you are given a 2D array fruits of size n cross n, where fruits ij represents the number of fruits in the room ij. So you can visualize like this. If this is a 2D array, then these values are basically the number of fruits in that room. Okay, so this would be the game, and this dungeon game is like there are three guys. One is standing here, other is standing here, and the third one is standing here. Okay, so one is on the very first cell, other one was the rightmost first cell, and this guy on here. Now what they have to do is they have to reach here. Okay, so there are movements given to us, that how do they move, okay, for all of them. So children make exactly n minus 1 moves. Okay, so every guy has to make n minus 1 moves only out of that. Okay, if there are n into n size this 2D array, then we have to make only the up to n minus 1 moves for every guy, all these three childrens, to reach the room number n minus 1, which is like this room. You can say this is the n minus 1 room, right? If there are n row and n columns are there, so they are tending towards here and collecting the fruits. Now there are the coordinate moves given to all of them. So let's say talk about child 1. This guy is starting from 0 0, and it must move from their current room ij to one of these. So these are the possible values, that he can move I plus 1 j plus 1, or I plus 1 j, or ij plus 1. Okay, this is something like this. You can visualize it like this guy, the one which is on very first, I plus 1 j plus 1, he can move like this, or ij plus 1, like I plus 1 j, or like this ij plus 1, right? So right, bottom, and the diagonally he can move in these directions. Okay, now next guy is the child starting from 0 to n minus 1 must move from their current room ij to I plus 1 j minus 1, I plus 1 j, and I plus 1 j plus 1. So what does it mean is basically he's talking about this guy. Okay, so he can either move to here, right, ij plus 1, or he can move like this, I plus 1 j minus 1. Okay, or there is one more movement, I plus 1 j plus 1. Okay, so if let's say somebody is sitting here, if this guy somehow moved here, then he can have also this guy also, I plus 1 j plus 1. So these three movement given to this guy. Okay, you can see here. So for any ij, so these this would be, you can visualize this guy can go I plus 1 and j minus 1, column is decreasing, or I plus 1 and j is same, or it can go I plus 1 j plus 1. So every time its I is basically increasing, right? Its I is every time increasing. Now we'll go to the third guy. The child starting from n minus 1 0 must move from this ij to I minus 1 j plus 1, ij plus 1, and I plus 1 j plus 1. So you guys can observe one thing here. For child 2 and child 3, you can see here that from ij, this guy can move I plus 1 and j minus 1. And correspondingly, this guy can move, the third one can move I minus 1 j plus 1, just opposite of it, right? Here it is becoming I plus 1 j minus 1, and here it is becoming vice versa, I minus 1 j plus 1, right? Similarly, if you look the second move of this guy, see here, this is second move, I plus 1 j, then this guy is making I j plus 1, and then third one is I plus 1 j plus 1, and this guy also I plus 1 j plus 1. So you can observe one thing here from these movement coordinates for second guy and third guy, they are looking like the transpose coordinates, right? The way which transpose would have been moved. What I mean to say is like this guy, okay, and this guy. So they are looking like if like whatever coordinate they are moving, that is the transpose equivalent of this, right? So like ij, then that guy is making move to ji effectively, right? So now here three things we have observed. Let's talk about the first guy, that we cannot move more than n minus 1. Anyone can move only up to n minus 1 moves, right, as per given in the question. Now you can see here that the guy which is starting at here, if he tries to move for any because he also given three possibilities, but if it other than this route, if he take any move to any other valid direction, then it would go beyond n minus 1, because see here the length of this diagonal is n, right? So move would be total n minus 1, 1, 2 and 3. You can see the length of diagonal is 4 and the move is becoming 3, right? So length of it is n and its move is n minus 1, and if he tries to go to any other movement, then he will not able to make the n minus 1 moves. It will take more than that to reach this guy, right? So for this guy, although we have the other way also to move other directions, but he has to go only for this direction, otherwise n minus 1 condition would be violated. So the first guy would be coming only on the diagonals. He can collect all these values which are lying on this diagonal. So that is first thing. Now the second thing we have observed, that one guy is here and another guy is here. We have seen their movement are like transpose equivalent. So what I mean to say is this guy, see, this guy also cannot come beyond this, right? This is the diagonal which the child 1 would be moving on this diagonal. Then child 2, which is starting from here, that guy cannot come out of this boundary, like though it has the valid moves, but if it goes beyond, let's say if it also reach here, then n minus 1 thing would be violated for him. And similarly for the third guy also, this also cannot go to this direction, means the upper half of the diagonal. See, this guy, this is the upper half, this is the below half of the main diagonal. So they will stay. So this guy would be stay only in the below of it, and this guy would be stay only upper of it. Why? Because then they would be violating the n minus 1 moves, right? So this is our basic idea. Now what we can do here is, first of all, we will do whatever the collection this guy would be do, because he has only the one move to go through all those diagonally elements. He will collect and come here. And another thing is, if we do we are starting from here, and if we are doing for the upper half of it, once we are done for this guy, what if we make the transpose of it? What I mean to say is, all these values, if I swap with all these upper values, okay, which we do in the transpose of it, then same method would be calculate for this guy, because this is a symmetric stuff. So how we can do that? We can do the rolling array. Rolling array means here we don't need the entire dp of n into n. We will go in dynamic programming paradigm, but we are going, for the sake of saving the space, we are taking the previous row and current row. Why? Because we are, let's say we have calculated the maximum value for this row, then this row itself would be used to calculate the maximum of this row, right? So for that reason we need only two rows. So we are using this previous row and the current row. Using these two rows only, we want to calculate our final maximum collection of the fruits. Okay, so this is how we would be proceeding here. We call it a rolling array method when we do this kind of previous row and current row evaluation. So first of all, guys, let's say we have a variable called total. So we would be having all the maximum sum into this variable. Okay, so now one thing is clear, that we know that for this child 1, the guy who is starting at this 0 0 position, he will go along this this diagonal, right? So he will collect all these values. So anyway, first of all, we will sum them up. So 1 plus 6 is 7, 18. So 18 and 16, it would be 34, right? So first of all, 34 is anyway for sure we have to have, right? So okay, well and good. Now what we have to do is, then we will look for this child 2, right? So anyway, this thing we are done, that for this diagonal we got the sum of them, okay, and we got it 34. Now we will look for this child. Okay, So this child, you see here that it should not go beyond this boundary, right? Okay, so only these are the values where this guy can move the child to, right, which is starting at here. Okay, so now first of all we are making the use of this previous row and current row, right? So you can see here when he is starting from here, we are using a dynamic programming. So dynamic programming means we are partially storing the result. Okay, so when he is starting from here, let's say to reach from this this location to this itself, it will take whatever is value already sitting there. So that is 4, right? So we can here mention that, okay, in the previous row 4, we are starting for this 0th row. Okay, because we have to fill first previous row, then we will start from the very first one. So first of all we are filling this previous row. Okay, so this is 4 where this guy is starting first of all. Okay, n minus 1, he is already sitting at this location, child C2. Okay, so 4 I have filled here, and other value, let's say I'm filling the negative values. You can say the minimum value. Okay, whatever is the minimum possible, integer dot min. Okay, so these value would be like this, infinite negativity. Okay, now so we have filled this 4. Now we look for that what all moves are allowed for this guy. Okay, for C2 I'm talking. For C1 we are already done. Okay, C1 gave us 34. You guys can observe for child 2. Okay, child 2 is sitting at 0 and n minus 1. This guy can move only to these possible values, right? You can see here he can move I plus 1 j plus 1, I plus 1 j minus 1, I plus 1 j, or I plus 1 j plus 1. This is possible for this guy, right? So like he can move in this way where I plus 1 and j minus 1, or he can move in this way where I plus 1 and j, or he can move like this, I plus 1 and j plus 1. These are the valid moves. But remember, this is the boundary. It cannot go below it. Okay, and these values are already touched by the C1, so not also these diagonal values. Okay, so these values are the only one where this guy has to roam, and out of them he has to pick the biggest sum. Okay, so now we will make that how do, so we will start from here, right? So anyway we have put here previous already now, right? So this previous we have already done now. So here we have already 4 we have put. Now we will start from I row equal to 1, right? This is our row equal to 1, because previous we will use to calculate the maximum of it. Now see here how this I would be basically moving. What would be the coordinates of moving it? Okay, so that we will write it down. So now you guys can observe here that we are starting with row equal to 1 here, because previous row we have filled here. Okay, so at third column we have mixed the maximum value as equal to 4. Now we are starting from this row equal to 1. So see here, from row equal to 1 till row equal to the very last one. Okay, less than n. So where would be our start column every time? So very first time where we are starting at here. Okay, so when row equal to 0, we started at column equal to n minus 1. When row equal to 1, we will start at column equal to this guy. But when row equal to 3, okay, I mean the third row equal to 2, should we go, this guy would be coming out of this boundary, right? It is breaking for this diagonal thing. Then which one we should take? So for example, at when row equal to 2, at that time either we can choose this or whatever is the diagonal value plus 1, right? So but as we know that we cannot go below this diagonal thing. Okay, so what we are doing here is, you can see here, if we do n minus row minus 1, okay, every time this would be giving us the diagonal value when we are coming from here. So for I equal to 0, this value would be n minus 1 only, right? Row equal to 0. So but when r row equal to 1, then this will come this column, right? And when row equal to this guy 2, then this would be this column, but this would be violating our stuff. In that case, what we have to do, we have to take whatever is there in diagonal, the right side of that guy we should pick, because we cannot go below it. So that is why I am using this maximum of n minus row minus 1 and row plus 1. So when this case arises, our max would be here, our max would be this guy, right? So for that reason I am using this formula. This formula is nothing formula, we can observe here, right? So this would be our start column every time. Okay, so we are starting from this row now. So then where would be our this value goes? So our for loop would be like every time column equal to whatever is this start row, start column we calculated at this here. Let's say I'm calling start column SC, and column has to go less than or equal to whatever the max boundary. Column is less than or n. Okay, so in this way we would be calculating. Now every time we are looking, you can see here these three possibilities, right? Out of these three possibilities, we will keep on filling our this previous row and the current row. Okay, with the help of previous row we will fill the current row. So you can observe here when we are starting with I equal to 0, right? So this I equal to 0 we have already filled in this previous row, right? So very first is 4 we have filled. Now we are coming to this current row, okay, and we are starting with I equal to this one, okay, this row equal to 1, because 0th row we have already filled here 4 as max, right? Now we are at here, okay, so this in the original array 8 is already there, and in previous we have found 4, so 8 plus 4 12 would be here, right? Then we are at here 7, right? So 7, and what was the maximum? So these are the three possibilities where we would have come from, right? So we would have come from, so 4 is here, right? From the previous, you can see the from the previous we are getting 4, and in this one 7, right? So 7 plus 4, this would be 11, right? So that's it, we cannot go further more, right? Our column would be stopped here because the condition would be here. Now we will go to the next row, right? So for the next row, this current would become previous, right? So we will write here, this would become now 12, and this guy would become 11. Okay, so let me make it, this is 11 and this is 12, right? Other value is negative, let's say. So this is the previous for the next row. Okay, now we are coming here at the row number 2. Okay, so at row number 2 our thing is again becoming like as it is. This current we are creating every time from new. So see here, in the previous step just above it was 12, and the current value in the original array is 12. So 12 plus 12, this would become 24, right? And the other values would be as it is. So see here, what is the max here? This is 11 only. These are the other negative values. So 24 we have found maximum once we were doing. So can we do further more? No. Now we are done. This is our last one value we can reach from this child 2, because these are the diagonal value which are already filled by child 1. Okay, so in this way we can do. So let me show you this code. We will go further, but we will show so far whatever code I have done. Okay, so see here, first of all we have created this total fruits variable, just like we created here also. So what we are doing here is, first of all we are taking the all values who are sitting at diagonal. See there, we are going on fruits I. So I means same coordinate, means all the diagonal values. So we have filled all the diagonal values, we have taken into total fruits. Now we have written a calculate max fruit methods. Okay, calculate max fruit method. This method we were doing the dry run as of now. So see here, we created this previous row max and current row max. Okay, initially we are putting everything in the previous row max, the integer min value, and the very first value which where we started, right? We started from n minus 1. This guy child 2 I'm talking about. So we started from this column equal to n minus 1 and row equal to 0. So initially we have filled this value, because to reach from this value till this value, obviously the answer in the DP would be 4. Okay, so for that reason I am putting first of all in the row last column equal to whatever was the last grid value on the first row. Okay, we started with this. Now we are starting from row equal to 1 to n minus 1. Why row equal to 1? Because previous one we have already filled here. So see here, here we are creating the current row, right? This current row every time we were creating whenever a new row is starting. So this current row max I created with the negative values here also. Okay, integer max values we are putting here. Now what we are doing here is, here we are finding the start column. Okay, because we have to take care of those indexes, just like we were doing here, that all the values will be above this diagonal only. So for that we are taking this n minus row minus 1 and row, whoever is the maximum, which we already explained, right? So we are taking that as a start value, start column that we have taken here. So we are starting from int column equal to start column less than and call plus plus. So we are taking the best previous here. So best previous is equal to what? Whatever we had in the previous row max on the same column, right? So like we did here, when we came to here on second column, we took the previous column max, right? So here on the exact above, whatever value we are adding to this one, right? So you can see here, whatever the best value we have taken it. Now we are checking these three possibilities. Okay, we have three possibilities, right, to move it. So one is like if this one, right, previous row of the column minus 1, right? You can see here for the child 2 we have these possibilities, right? I plus 1 j minus 1, I plus 1 j, I plus 1 j plus 1. So for all these possibilities, when we reached at any column, we are looking for those previous value. So initially what we have done, in best previous value we have taken whatever was the right in the previous column just above it. Okay, whatever value we have taken, we are taking in this. Now we are looking for the two more possibilities, right? Because we have three movement values, right? So see here, we are looking for this value, that hey, are we getting further best? We have taken one of the movement best value here. Then we are taking the next value into this column minus 1, because that also could be the previous way from where we are coming to this column. And similarly we are checking for this column plus 1 as well. So this best value we will taken out of these four movement, the best value coming to our best previous here. Okay, now after doing this, what we are doing is current row max would be what? Whatever is the best previous plus the current value in the original array, right? So this is what we are doing. Once we are doing current row max, we are here, see, we are swapping the values like we did here. Once row was completed, we moved all the current row value to the previous value like this, and then this emptied every time. Okay, so once we are done with this, we are returning the previous row max value, which would be at the very last n minus 1 column. Okay, so this method is the calculate max fruit for child 2, right? Child 1 we diagonally collected, child 2 we are using this method. Okay, now you would have a question, where is child 3 then? Child 3 also has to make the movements, right? So see here, we are done for child 1 here, we are done for child 2 here. Now where is the child 3? So for child 3 you can see here this piece of code. Okay, what we gonna do here is whatever value are there, value this diagonal. Okay, those values we are making the transpose of them. Okay, so if I move all these values, value this diagonal, right? If I make, then if I swap all those values to corresponding, like say if somebody is sitting on ij, let's move to them ji, swap them. Okay, so if we do that swapping would be basically giving us the transpose of it. So in that case what will happen, because this portion and this portion both are symmetric. Okay, so if we do the transpose, means if we move all these values to the top of it and these values to the below with swapping operation, then we can use the same method, the one which we have just used. So see here what we are doing, we are swapping all those values. You can see here ij moved to ji, so all of them would be whoever value the diagonal now would become to the upper of the diagonal. And same method we are calling again after updating this one. So total fruits equal to again that calculate max fruit method we have called. So now we have done the child 1, child 2, and after making the transpose of this 2D array for the child 3 as well. And then in the total fruits we are returning the value. So this is how we are doing. And what would be the time complexity? The time complexity would be O of n square, and space complexity is O of n only. Okay, see here we are taking only these two row. Okay, this would be like even every time we are swapping them. So we are interested only row wise. So we are taking whatever number of the values are there, only O of n would be the space complexity. So let me execute my code. Yeah, so I am doing it, which I have already submitted, but still for the sake of video I should do that again. So yeah, so yes, it is accepted. It was kind of 75% faster. So thank you for watching this video, and if you guys have any concern, please make a comment over there. Also take your pen and paper and make sure that whatever I am saying is like you have visualized clearly or not. Okay, so thank you.